Like, subscribe, and hype the video. Also, leave a comment on any topics you want to hear about in the future. Okay, let's dive in. In our last episode, we walked through the full case for the simulation hypothesis, Bostrom's logical trilemma, the technological trajectory argument, the strange quantum properties of our universe that resemble computational architecture, and the reasons serious credentialed figures across multiple fields put meaningful probability on this idea rather than dismissing it outright. Today, we're getting into the other side. The serious substantive objections from physicists and philosophers who've looked at this argument carefully and found real problems with it. The question of what it would actually mean for how you live your life if it were true. And the one implication of the simulation hypothesis that almost nobody discusses, but that might be the most unsettling part of this entire framework. Let's get into it. The most direct, most technical objection to the simulation hypothesis comes from physics, and it's worth taking seriously because it's grounded in real calculations rather than intuition. Simulating a universe at the level of detail we actually observe, down to individual particles interacting according to quantum mechanical rules, requires an almost incomprehensibly large amount of computational resources. Physicist Zohar Ringel and colleagues published research in 2017, arguing specifically that a perfect quantum simulation of even a modest physical system would require more computational resources than exist in the observable universe itself. Because the complexity of quantum systems scales exponentially with the number of particles involved rather than linearly. In other words, you can't simulate a universe using resources from within that same universe. You'd need a simulator dramatically larger and more powerful than the thing being simulated. Proponents of the simulation hypothesis respond that the simulator civilization wouldn't need to simulate every particle in full quantum detail everywhere simultaneously. Just as a video game doesn't render what you can't see, a simulation could use computational shortcuts, only calculating full detail where and when it's actually needed for consistency. But critics argue this kind of selective rendering would produce detectable inconsistencies or artifacts, observable glitches in the physics that we haven't found evidence of. Like, subscribe, and hype the video, and let's get into the philosophical objection that cuts even deeper. One of the most fundamental problems with the simulation hypothesis from a scientific perspective is that it's extraordinarily difficult to test in any meaningful way. For a hypothesis to function as science rather than philosophy, it needs to make specific predictions that could, at least in principle, be tested and potentially proven wrong by observation or experiment. The simulation hypothesis, in most of its formulations, is remarkably flexible. Almost any observation can be accommodated within it. Strange quantum behavior, computational optimization, the speed of light as a universal limit, maximum data transmission rate, fine-tuned physical constants that seem suspiciously well calibrated for life to exist, deliberate design parameters set by the simulators. This flexibility is intellectually suspicious. A hypothesis that can explain anything without being contradicted by anything isn't really making testable predictions. It's providing a framework that absorbs all possible evidence without ever being threatened by any of it. Some researchers have proposed specific testable predictions that a simulated universe might produce, such as detectable minimum resolution limits in the fabric of space at the Planck scale, or subtle systematic errors or artifacts in the laws of physics that might reveal underlying computational structure. So far, none of these proposed signatures has been definitively detected, though proponents reasonably point out that our instruments may not yet be sensitive enough to detect them if they exist. Here's a question that most discussions of the simulation hypothesis skip past too quickly. If we somehow confirmed tomorrow morning that we were living in a simulation, what would actually be different about your life? The answer, when you think about it carefully, is probably less than you'd expect. Your experiences, relationships, and emotions would be equally real to you regardless of whether they're running on biological hardware or computational hardware. The pain of loss, the warmth of connection, the satisfaction of achievement would all function exactly the same way inside a simulation as outside one, because from your perspective as an entity inside the system, there is no meaningful difference. The food you eat, the people you love, the work you find meaningful, none of that becomes less real simply because the substrate it's running on turns out to be different from what you assumed. This is actually one of the more grounding observations about the simulation hypothesis. Even if it's true, it doesn't change the practical or experiential reality of being a conscious entity living a life. Whatever meaning and value exists in your experience exists independently of whether the hardware underneath it is biological or computational. Like, subscribe, and hype the video. And now let's get to the implication that almost nobody discusses, because this one genuinely unsettled me while writing it. Here's the part of the simulation hypothesis that most popular discussions leave out, and it connects back directly to the Fermi Paradox we covered in an earlier episode. If simulations are possible, and if a technologically advanced civilization can run them, then the total number of simulated universes and simulated conscious minds that could ever exist is essentially unlimited, bounded only by the total computing resources available to all civilizations throughout all of time. Now combine that with Bostrom's first option from Episode 1, the possibility that virtually all civilizations go extinct before reaching simulation-capable technology. If that option is the true one, it means the overwhelming computational potential for simulation never gets realized, and the ratio of simulated to biological minds stays low or zero. But here's the uncomfortable connection. If that first option is true, if civilizations reliably go extinct before reaching this technological threshold, then we're back to the great filter sitting somewhere in our future rather than our past. The simulation hypothesis and the Fermi paradox, two of the most discussed ideas in this space, actually point at the same underlying uncertainty from different directions. Either civilizations survive long enough to run simulations, in which case we're probably simulated, or they don't, in which case there's a catastrophic filter waiting for technological civilizations, and we're approaching it. Neither option is particularly comfortable, but together they suggest that one of the most important questions we could possibly answer is whether advanced technological civilizations tend to survive long-term, and we currently have almost no data to go on. So here's an honest summary of where the simulation hypothesis actually stands. The philosophical argument is more rigorous than most people realize, structured as a logical trilemma where at least one of three options must be true. The technological trajectory case is genuinely compelling when you take modern computing trends seriously over very long timescales. The physics similarities are interesting but ambiguous. The features of our universe that resemble computational architecture also have conventional physical explanations that don't require simulation. The objections are real and substantive. The energy requirements for a perfect quantum simulation are genuinely enormous. The hypothesis in most forms is very difficult to test in any way that could convincingly falsify it. And the specific physics signatures that a simulated universe might produce haven't been detected, though our instruments remain limited. What the simulation hypothesis ultimately represents, in its most honest framing, is a question about the nature of reality that current science genuinely cannot answer, and may not be able to answer for a very long time, possibly ever. It sits at the exact boundary between philosophy and physics, in a region where our tools for distinguishing true from false are still catching up to the questions being asked. So here's where the simulation hypothesis leaves us. It's a serious, structurally sound philosophical argument with genuinely interesting connections to modern physics, endorsed by credentialed figures who've thought about it carefully, and facing real substantive objections that haven't been fully resolved in either direction. It may be the most important question nobody can currently answer, and the answer, whatever it turns out to be, carries implications for everything from the Fermi paradox to the long-term future of our civilization. Whether we're living in base reality or inside someone else's computer, one thing remains constant: the experience of being here, thinking about it, and wondering. That part is undeniably real, whatever real actually means. If you've made it through both episodes, let me know in the comments what you actually believe, and whether this changed your thinking at all. Like, subscribe, and hype the video, and I'll see you in the next one.